In this video, we introduce our CVPR2022 work, Projective Manifold Gradient Layer for Deep Rotation Regression. In this work, we tackle the problem of rotation regression, which is an important task in computer vision and has a wide range of applications, such as object pose estimation, camera relocalization, robot control, etc. Recently, deep neural network-based rotation regression has drawn much attention. Compared to other estimation approaches, regression has several advantages, including end-to-end, running fast, plug-and-play, etc. However, it is very challenging for a neural network to directly regress a rotation. We know that the rotations lie on a non-Euclidean manifold, SO3. But the raw output X of a neural network with linear activation lies in the Euclidean space. Thus, a projection function pi is needed to transform the X onto SO3, which is in nature a many-to-one mapping. Most previous works focus on improving rotation regression by changing the rotation representations along with the corresponding pi functions. They propose several regression-friendly rotation representations, including 6D, 9D, and 10D, in addition to classic quaternion. However, one critical design space that has been long neglected is to improve the backward pass. In the right figure, we denote that X is the network raw output, which is projected to a rotation R on SO3 by the pi function, and Rg is the ground truth. For the function pi, we show the inverse image of R as the dotted line, where all X along this line will be projected to the same R. We can then derive that the classic gradient by chain rule is always perpendicular to this dotted line since changes along this line don't affect R. However, to update the current output R to the target Rg, the shortest path, denoted as the red arrow, is along the vertical to Rg's inverse image. Therefore, the classic gradient is suboptimal when considering the whole optimization process. Based on this observation, we propose a novel projective manifold gradient to improve the optimization in the backward pass. We first compute the Rg's inverse image and then find xgp in the inverse image which is closest to X. Then we let our gradient be X minus xgp, which we call the projective manifold gradient. There are several issues to fix for this PMG. The first one is that in some scenarios the ground truth rotation may not be available. For example, in self-supervised learning, the supervision may come from chamfer distance loss. The second issue is that, when R is far from RGT, the projected point xgp can lie in the opposite direction to RGT and lead to a 180-degree error. To fix the two issues above, we propose to leverage Riemannian optimization, which can return and update Rg on the geodesic from R to RGT. The distance from R to Rg can be controlled by a hyperparameter tau. Rg can be computed even when RGT is unavailable. As for the second issue, we can use a small tau to keep Rg close to R, alleviating the reflection problem. The third issue we find is vanishing length. Due to projection, our PMG always tends to reduce the length of X. The right figure shows that the length of X keeps decreasing during the training. This will increase the effective learning rate and is thus harmful to achieving convergence. To fix this issue, we add a regularization term, lambda xgp minus Rg, which penalizes small lengths. The right figure shows that after this fix, the length remains almost constant during the training. Here is the overview of our pipeline. We first use Riemannian optimization to compute a goal rotation Rg on SO3, and then use inversion and projection to find the best xgp. The final regularized projective manifold gradient is then computed and directly backpropagated to the network weight. Here we show 5-degree accuracy for rotation regression. The left shows the result on point cloud while the right is for images. We can see our gradient layer brings significant and consistent performance to all the considered rotation representations. Our method also works when GT rotation is unavailable. Our method can be further applied to other non-Euclidean manifolds, for example regressing unit direction vectors that lie on S2. In this work, we propose a plug-and-play gradient layer, regularized projective manifold gradient layer, to improve the backward pass of deep rotation regression and bring significant and consistent performance improvements to rotation regression for many rotation representations at zero or minimal running time and memory cost. We have released the code. Thanks for watching.